Well, from what we've been doing, I guess you could see this was coming up, solving non-right angle triangles. In other words, all this work up here with Pythagoras and trigonometry in the 90-degree triangle is a bit limiting, isn't it? There are a lot of circumstances where we have this sort of situation with 90-degree triangles, but there are many others. Let's look down here where there's no 90 degrees in the triangle. So the old SOHCAHTOA, here it is here, it was great for 90-degree triangles. Sine is the opposite over hypotenuse, cosine is the adjacent over hypotenuse, tan is opposite over adjacent. That was good. And you could see it will always work, because look at this row of triangles here. One is the enlargement of the other. So the ratio as you enlarge this triangle to this one, the ratio around a given angle, this one is 30 here, stays always the same, because the proportion by which, or the factor by which the sides increase is the same in the process of enlargement. Just a little bit of revision of why sine, cosine and tan work in a right angle triangle. All right angle triangles with a fixed angle there are identical, are similar figures produced by enlargement. Okay, well, we're going to leave that now and see what we can do in a non-right angle triangle. So come over here, and we've done this, of course, redefined in a consistent fashion the sine and cosine. The sine is the y coordinate, here it is here, and the cosine is the x coordinate of that point on the circumference of the circle as you rotate the angle theta around. It's consistent, here it is, it's consistent with SOHCAHTOA in the first quadrant, but it does allow you, look over here, to extend to an angle bigger than 90. And therefore have a new point, let's call it Q, which has an x and a y, and that will be the sine and that will be the cosine. So what about these triangles over here? Can we do anything with those? And there's no 90. So our task now is to build from SOHCAHTOA into a situation where we can work with relationships between sides and angles in triangles like this. Like this one hasn't even got any angles. Is it possible to find the angles given those sides? This one's got one angle and two sides. Can we find the other side? Let's do some maths now and see if we can find a rule for triangles which don't have a right angle in them. This is exciting stuff now. So here we are. Here's our problem. What about working in non-right angle triangles? How could we do it? There are our two, and I guess you could start to go back to SOHCAHTOA and maybe try some of this. Okay, let's see what we can do. Can we develop new rules? New rules that don't need a right angle triangle. Is that possible? Well, I guess you say, well, honey, of course it's possible, otherwise you wouldn't be talking about it. And you're right. Okay, let's go down and have a look now. And here, the law of sines, or the sine rule. This little screen clipping here comes from Pearson's textbook, published in the UK. So I've taken a couple of screen clippings here, and let's have a look now at starting with the area of a triangle. It says here, we've done that in a previous section of the work, and yes, we have. The area of the triangle is half the product of two sides, sine of the included angle. Just remember that generic interpretation there. Half the product of two sides, okay, and then times the sine of the included angle. Can I write it like that for you? Okay, so it doesn't have to be these particular sides and that angle. It can be any pair of sides. So here's our little triangle here. It could be a half that times that sine of that angle, or it could be a half that times that sine of that angle. I hope you've done that in your earlier work, in the earlier presentations. I hope you've practiced it. Now let's do a little tricky do here. Let's divide each of these expressions by a half ABC. There it is, dividing it by a half ABC. Okay, And what do we get now? If we divide that, have a look, the halves go out in that one. You get sine c over little c. The halves go out, the a goes out, the a goes out, c goes out, c goes out. You get sine of angle b over little b. Can you see what's happening? B and c cancelling. So you get the sine of the angle over the side opposite is constant. Okay, could we do that? Write that in words. A generic result again. The sine of any angle in the triangle divided by the side opposite is constant. Okay, they're all the same. If you do that for each angle, find its sine and divide by the side opposite. See there? Sine C over C. Sine B over B. Sine A over A. Interesting result. I think we have just done it. Okay, so here it is. We usually call it the sine rule. It's the law of sines, if you like, and this is what just happened. Okay, now that might be the most useful way to find an angle. Have it that way up, because you might be looking for the sine of angle A, and you might know the side opposite, you might know another angle, and its side opposite, and you want to multiply across to get sine of A. But what if you wanted to find a side? Let's invert or find the reciprocal of each. So turn them upside down. So if you have the side on top over the sine, and they would all be the same if you found the reciprocal of each one. Okay, so this might be useful, this form, to find a side. Because you usually, when you want to find something, want the unknown to be in the top. And then if you knew that one and that one, you could just multiply across. Okay, so you might choose to use it in either way. Let's have a look at the idea of that. So here's finding some sides. Find the length of AC, here we are, to 2 decimal places. Do we know enough? Well, we have the side, the angle opposite it, and we have another angle and its side opposite, so we should be okay. Because we should be able to say, what do we want? That's little b, isn't it? Opposite b. So little b on top over sine b. We're using the sine rule this time with the side on top because that's what we want. And it would be the same as any other side on top of the sine of the angle opposite, which would be little c on sine of big C. And then multiplying across, there we are, we can work it out and round it off. Notice the use of the approximate sign, or this one, and we really should put 2 decimal places in brackets there. Okay, that's what was asked for back over here. Alright, get the idea? Here, have some. Have a go. And you're looking for sides here. Okay, so in each of these, remember the rule. The idea of the rule is the side divided by the sine of the op angle is constant. So you compare any of them up. So you need to have some. And this one and this one, this one and this one. Not a bad little tool. I would suggest you draw your triangle carefully here, because find little a, that's opposite big A. And just remember, little b is opposite big B. I draw the triangle so that you can see what's going on, and you're looking for this idea. All right. Okay, pause the presentation. I suggest you all of them. There's not too many here. And I'll go down now and show you the answers. Here they are. I hope you got those. All right. Well, that's an interesting rule, isn't it? And I wonder if we could find angles now. Let's do it the other way up. So we want the angle. Okay, so the other way up. And we've just used that. But what we're going to try and find is an angle. Now, this is called, this little section here is called the ambiguous case. So if, for example, I gave you 43 degrees there, and we tried to work this out using the rule like that to find an angle. Let's try to find this angle, because we've got it side opposite. So we could say, let's say that's theta. Sine theta over 10 is equal to the sine of 43 over 7. So the sine of theta equals 10 times sine 43 over 7. Or theta is the inverse sine of all of this. Use a bracket, but just make the one entry on the calculator. Okay, and if you do that, theta is almost exactly 77 degrees. Okay, you might look at that and say, gee, that looks bigger than 77. And then you might remember, hang on, there's another angle that could be in the triangle. Let's just do this unit circle. 77 in there would have a sine which is the y coordinate. Hang on, there's another one over here. Do you remember that would match up if that's 77 in there? So the actual angle is that big one, 180 minus 77. So this is what's called the ambiguous case. Okay, it could be 103. Okay, you'll always get the acute angle coming off the calculator. Hang on just a minute there and we'll fix that up now. Sorry about that little glitch there. So what we're saying here is this angle over here is actually 180 minus 77, or 103. Okay, that's what we're talking about there. So instead of just the acute angle coming off of the calculator, got to remember, I'm putting it in blue now, this is the ambiguous case. It could be that one, or it could be 180 minus that one, which is 103. And actually in this situation, it does look obtuse, doesn't it? It looks bigger than 77. So because this is not a scale drawing, you can't actually do it that way. You should quote the two answers. So this is the ambiguous case. When you're looking at finding an angle with the sine rule, you've got to watch out for, could it be bigger than 180? Now, this one could, because see how it's opposite the biggest side? So the biggest angle, the only one that can be bigger than 90, is going to be opposite the biggest side. Now, you can't have more than one bigger than 90, because the sum of angles of a triangle are 180. Let's just review that. So in this triangle, there'll only be one. That's got to be the biggest one. That could be bigger than 90, but then there's less than 90 left for these two. So there's only one that could be bigger than 90. It will be opposite the largest side. Okay, so that's the ambiguous case. When you're looking at trying to find the angle and it's opposite the biggest side, you have to quote two answers. Let's look at it a little bit further there, down here. Okay, let's see how it happens. Let's say you start here with this baseline and you draw up here 43 degrees. Then you go out and you fix this point, so that's fixed. Okay, now how can this point lie in more than one place? Let's have a look. We have this fixed point at the end of 10, swinging off at 43. Now how many lines, 7 centimetres long, can you draw? Let's throw an arc. Let's put the compass point there and draw a circle. 7 units long. Okay, a bit wonky, this circle. Something out there like that. So coming down here, let's have a look. Would this, oh yes, there's our problem. There's our problem. When you specify 43, 10 and 7 in that way, where the angle is opposite that 10, the biggest side, you could get that one, which is our 103, or it could have been this scenario. And we don't know, because you're not allowed to just look at that on a diagram, because most of these diagrams are not drawn to scale. Can you see the idea? It is non-unique. when you swing an angle of 43 and go out 10, that 7 could be either of those scenarios. Let's look at the diagram down here then. Here it is. So there you are. And you don't know except by inspection. Inspection or looking at it. Oh, no, hang on, I better put this in here, 43. We shouldn't do that because the diagram is not to scale. Okay, it's not to scale. All right, so we've got to quote 2 answers, or perhaps use a different rule to find that. Okay, here it is. Using the sine rule to find the largest angle leads to ambiguity. 2 possible answers. So we try to quote those 2 answers or find another way of getting that biggest angle. And remember, the largest angle is always opposite the largest side. So if you've got a side bigger than another, and it could be the largest, then try not to use the sine rule to find that, because you have to quote 2 possible answers. It's ambiguous. Okay, you don't know which one it is. You can't go by looking at the drawing because it's not to scale. Okay, let's have a look at doing some angles now. Find the measure of angle C in a triangle ABC if AC is 7 and AB is 11 and angle B measures 25. Okay, by the sine rule. Let's draw it here. First of all, angle B has a side opposite 7 and angle C is opposite this one. So we're going to use that angle and that one. Now, so sine of the angle over the side opposite is the same for each of them. And we use it this way up so we can just multiply across. Multiplying across, then putting on the calculator as I did before, you get approximately, because you rounded it off, 41.61, 2 decimal places. But you don't know, C may be obtuse. Why? Because look back over at the diagram, this is bigger than this. Okay, may be obtuse because it's opposite the largest side that is there at the moment. We don't know what side, what size that is. Okay, so there's ambiguity here. You should quote the angle in the first quadrant, which is what's going to come off of the calculator, and then 180 minus it. Okay, and you state those answers. And you don't know enough about the shape. So in other words, it could be the 4161, or it could have been in here somewhere, and that would be the other one. Same idea. This 7 centimetres swung could hit this line in 2 different places, and we don't know. You can't use guesswork because that, or inspection, because that triangle is not drawn to scale. Have you got it? I want you to try some for yourself now. We'll do this another example though. We've got triangle KLM, and LKM measures 56, LM is 16.8, KM is 13.5. In this situation, you can only find L. You've got to have the side opposite. So the sine of angle L over side opposite is the sine of 56 over its side opposite. Multiplying both sides by that, there we have it, straight on the calculator. So it could be 41.77 or 180 minus it. But, hang on, this is not opposite the largest side here. This angle 56 has 16.8 opposite it. So L only has 13.5, it's going to be less. So here, therefore, L is this one. Or you could reject this because 138 plus 56 is already there, is greater than 180, which is impossible. But it really comes back to, is it opposite the largest side? And this time L was not. There's the largest side. L is opposite this one, and so it's not going to be bigger than 180. Alright, so want you to work through these problems now, finding the angles using the sine rule, and finding the 2 possible values, or sometimes there won't be 2 possible values. You'll be able to say uniquely what it is. So I want you to go through and try those now. Okay, so try these first 4. Pause the presentation. And then I'll show you 5, and then I'll show you the answers. Okay. And here they are down here. Okay. See how you went? Did you get the 2 options in the ambiguous case, where you're trying to find an angle which could be the largest in the triangle? Make sure you quoted those. All right, let's move on now. And, oh, there's another rule. I wondered if you realise we do need another rule, because see this triangle, we can perhaps do something with this if we knew another angle. But we don't. We need another rule. We can't use the sine rule for this one. T over the sine of 80 is 17 over... No, don't know it. Or 13 over... Oh, don't know it. And over here, no angles at all. This is where we need to develop another rule. Let's have a look at the proof for that now and see what we come up with. Okay, using a bit of coordinate geometry here. So let's put our triangle so that one of the vertices is at the origin. And then what we could say is, you dropping that perpendicular just for this derivation, we could say here the x-coordinate of this point, the x-coordinate is that. The x-coordinate over b is the cos of angle C. So it's b cos C. The y-coordinate over b is the sine of C. So y is b sine C. Okay. And then if this side is A, point B is going to be A naught. And we can do the same situation over here, and that will still be the same even if this angle here, angle C, is obtuse. Okay, well, let's try to do some Pythagoras now. Okay, so this side, so in this triangle here, we've created a 90. Just to explore this, we don't want to do this every time, it's too much work, we're going back to Sokotoa. But c squared by Pythagoras is this squared plus this squared. Okay. So, if you do that then, by Pythagoras, well, sorry, it's not that, it's b cos C, b cos C, take A, okay, for the length there, and b sine C, take naught, the 2 lengths in that triangle to get the c squared. Okay, so then if you square both sides and expand them, just twice the product there, what's that? Twice the product, and get all the expansions happening there. Then you can factorise out b squared, and out of this one and this one, and get cos squared plus sine squared. Take 2ab cos C plus a squared. Now cos squared plus sine squared, we've had before, comes to 1. Okay, so this becomes b squared times 1. Take 2ab cos C plus a squared. So in other words, c squared is a squared plus b squared, take 2ab cos C. In other words, we have got a rule which is independent of that altitude, independent of the height there. We used it to create a right angled triangle, but now we don't need it. Okay, we've got a relationship without that in it. Okay, so just watch, you can go through this again, I've gone through it fairly quickly here, and just make sure this diagram is just the obtuse case, but because these are the same, you can use the same algebra. Alright, so there's our new rule. Let's have a look. Here we are, law of cosines. Well, they've done it in 3 different ways. Why? Because it's generic. Okay, what do you mean by that? Well, if you've got this triangle, what is it? You choose the side opposite the angle. C squared is the sum of the squares of the other 2 sides minus twice their product by cos of the angle opposite. So that's the pattern. So we did C, but can you see B squared would be sum of the squares of the other 2 sides minus twice their product by the cos of the angle opposite the side you've chosen. So you've got to know an angle and two sides, and then you can get the side opposite that angle, no matter where it is, because this is a generic pattern. It doesn't matter which one you choose, that relationship is going to be the same, because we could have put the perpendicular from any of the vertices. All right, let's have a look at using it. Here we are. Find correct to two decimal places the length of BC. Can you do it with a sine rule? No, because you don't know other angles. Okay, so can you use a cosine rule? Yes. The square of any side is the sum of the squares of the other two minus twice their product by the cos of the angle opposite. If we go through that process, we have BC is approximately that, which is 8.80 in two decimal places. All right, so we're starting to build up some ability in triangles that don't have a right angle, but we need certain other information, don't we? Okay, so use that formula now to work out the missing side here. You've got to know the other two sides and the angle opposite the missing side. So each of these rules have their own requirements. There's some answers. Okay, let's go on and have a look at rearranging this. So we have this rule, but what if we want the angle? What if we know all the sides and want to find some angles in there? Let's rearrange it. So putting 2ab cos c on the other side, making it positive, it equals a plus b squared takes c squared. So we're going to put that over there. Okay, dividing through by 2ab, we got cos of c is that. Hey, that's not too bad. Or putting on the calculator inverse cos. What's that saying over here? If I choose to find angle c, it's the sum of the squares. Okay, here let's write this down. Sum of squares other two sides minus square of the side opposite the angle you're trying to find divided by 2 times the product of the other two sides. So trying to put in words. Let's do it over here for angle A, let's say. That would mean cos of A is sum of the squares of the other two minus twice their product cos of the angle opposite. Sorry, hang on. I've got mixed up here. Sum of the squares of those two minus the opposite over twice the product. The cos is that. Okay, and you can do it for any angle. It's the sum of the squares of the sides around it minus the square of the side opposite over twice the product of the sides around it. A generic approach here. Do not get fixed in ABC land, because I could give you a triangle PQR. And what would P be? What would Q be? Q squared would be P squared plus R squared, take 2PR cos angle Q. Have you got it? Or cos, it's tricky a bit, cos angle R is what? P squared plus Q squared, take R squared over 2PQ. Have you got the idea? Okay, practice that. Think about a generic or a word approach to the definitions. And there they are, of course. Or the different versions using that generic approach. Okay. All right, let's go down and have a look at some problems. This time we're going to find an angle. Okay, find the measure of that if we know 3 sides. Okay, so we pop in here. Let's find angle C. Cos of C is the sum of the squares of the sides around it minus the opposite. So there's always a relationship in the cosine rule, again as it is in the sine rule, the side opposite and the angle. They are the related values that you have to think of. Okay, working it through, you get 60. Alright, so here's a question for you. Will the cosine rule lead to any ambiguity in the largest angle case? Well, let's have a look. The largest angle might go into this quadrant. Let's have a look and make it a theta there. So this angle is 180 minus theta, like before. Now this point has an x and a y. Uh-oh. What do you notice? The x is the cos, but the x has gone negative. So if you have an angle you find in the first quadrant, what was it before? 77, and it's really 103, this one over here. Okay, will you be able to pick that up with the cosine? Yes, you will, because the cosine of 103 in the next quadrant will be a negative. And when you put that calculation on the calculator for the cos, you'll have a negative, and the calculator will give you an obtuse angle. It will tell you, because the cos, as you go through that 90-degree position into this quadrant, becomes a negative x, and a negative x implies a negative cosine. Okay, so you don't get ambiguity with the cosine rule. So if you can use the cosine rule to find the largest angle, you will know definitely, without any ambiguity, whether it's bigger than 90 or not. Okay, let's have a look. Come down here. A few problems. There's question 2, 3 and 4. These screen clippings are from Hayes and Harris publications for Year 11 Trigonometry and Geometry. It's good to have that book handy by. Okay, have a go. I'll show you the solutions in a minute, or the answers rather. Here's number 5, which is a bit harder. Okay, now the answers. There we are. All right, let's move on. We've got a little bit left here in using the rules in an application, so let's bring this up here. Now, what I want you to do is to have this problem-solving strategy. You always start off by trying to find a right-angled triangle and use Pythagoras, if you've got enough information. Or using a right-angled triangle. Remember, we're trying to use the simplest approach, which is Pythagoras and SOHCAHTOA. You're looking for that first. Then, if you haven't got that, you could use the cosine rule or the sine rule, depending on what you're given. So if you're given 3 sides or 2 sides and an included angle, use cosine rule. If you're given 1 side and 2 angles, sine rule. Or 2 sides and a non-included angle. But look out for the ambiguous case, when the smaller of the 2 given sides is opposite the given angle. Okay, or in other words, one of the other sides, or one of the other angles could be the biggest one. Okay, so go through and think about what you've got and which rule you choose, but try to use right-angled triangles in the figure, because the SOHCAHTOA approach from Pythagoras is easier than these 2 rules to apply, isn't it? All right, come down now and let's have a look at some problems. Here's a practical problem now. The angle of elevation of the top of a mountain measured from 2 beacons, that one and that one, 2 different angles. And if the beacons there are 1473 metres apart, how high is the mountain? Okay, well, let's have a look at what they're doing first. Angle ATB, that's that one in there, is 11.5 degrees. Okay, so here we're working with that one, because if you look here, the exterior angle of a triangle, that one equals that one plus that one. So taking those 2 away, 11.5. We can now find an angle in triangle ABT, that one, this one here. We've got that, we've got that, and we've got that. So using the sine rule, we can pop into here. Okay, x over the sine of the angle opposite equals 1473 over the sine of its angle opposite. So we've got an approximate value. Keep all those figures, because we want to go on and find the height now. And what will you do? Well, you're in a right angle triangle. So when you come into this, you immediately think Pythagoras or SOHCAHTOA. So let's do it. Sine of 41.2 is opposite over the x. This is what I call a go-between problem. You've got to go between 2 triangles to find your first answer. This triangle first, and now you're popping into this one. Okay, transferring it across, going between. So the sine is h over x. Keep all the figures on the calculator, and then What we've got then is sine 42 times x. So we've got sine 42 times that will be h, because we've got h over this number equals h over x. All the figures equals the sine of 41.2, and then multiply it across. So h equals sine 42 times that. And then round it off. We've got 4 figures here, or round it off to 3 significant figures. So this is going to be helpful in going between a triangle which doesn't have a 90, but we can now solve it, and popping into the next one, which may or may not have a 90. Have a go at some problems, more complicated problems here than what you've done before. You're getting a lot more skills now, aren't you, in being able to work in non-right angle triangles. All right, there's the first 3. Pause presentation, have a go. Show you the answers in a minute. All right, come down, a couple more here. Oops, just go back up here a little bit. So 4, 5, 6 and 7. So pause it and have a go, and let's have a look at the answers. All right, so there's some answers for you. How are you going with all of this? Hope you're going well. Let's go onwards now. Have a look at a 3-dimensional problem. Same idea. Find the measure angle RPV. RPV in that slopey triangle in there. All right, so we've got a lot of work to do, a lot of go-betweens. We don't know anything about that triangle, but we know a little bit about this here. So let's go in RVW, so we're in that triangle. I like students to draw it out again, so you can see what's going on. So you can get there, the RV, so that's a go-between, you can get that by Pythagoras. PUV, you can get PV, so that's this triangle, so you can get PV. Again, try to do the simple right angle stuff first, and then in PQR, so PQR is up here, in this triangle in here. It's good to draw them out again. So if you've got PV, you can go into that triangle, and 6 squared plus 5 squared is going to give you root 61. So that's in triangle PQR. Sorry, I've shaded the wrong one in here. So I've got this one up here now, PQR. You can go into that one. So you've got the 3 sides now by working in those 3 right angle triangles. So can you find the angle RPV? What is RPV? It's this one here. If you call that theta, what's the rule say? It's the square of the sides around it, some of the squares around it, so here they are, redrawn down here, minus the square of the one opposite it, over twice the product of the sides around it. Okay, when you work that through, don't go to decimal yet, put cos neg 1 of the bracket, approximately that angle. Okay, have you got it? You do quite complicated work with go-betweens now. Okay. Come down and have a go at some problems. 8, 9, 10, 11. Pause it and have a go. Okay, and 12, 13, 14, 15. Heron's formula. Okay, we saw that before, and now this is a proof of it. So I want you to have a look at that. So I'll come down just a little bit. There. And then I'll give you the answers. Heron's formula is a proof, so they haven't got that on there. Well, that brings us to the end of trigonometry, basically. Now you can work not only in right angle triangles, but non-right angle triangles, and you can calculate lots of stuff there. So I hope you've enjoyed that. Hope to catch you in another presentation. Cheers for now.